Okay, good morning. So today we are going to look at modeling. Now, software modeling is something that you have addressed earlier in your previous software engineering modules, I believe. And in this week, we are going to mainly look at the architectural aspects of modeling. So you might have covered UML in your previous lessons. In your previous courses, but here we will learn, in addition to UML, other modeling techniques will be discussed as well. So the objectives of this lesson is we are going to look at what is modeling and how do we choose what to model, what kinds of things do we model, and how can we characterize models. Then how can we break up and organize models? And how can we evaluate models and modeling notations? So at the end, we are going to evaluate, like compare different models, and you should know how to select from among the various types of models. When you are given a project, you have to select which modeling technique would be beneficial for the given project. Then, for example, we will look at concrete examples of many notations used to model software architectures, and we will revisit our Lunar Land game as expressed in different modeling notations. So first, let's look at the definition of what is architectural modeling. So in the previous lessons, we learned that architecture is a set of principal design decisions, right? Principal design decisions. So we are not going through all the small design details in the architectural modeling. So you don't need to specify everything. So you have to decide what are the important aspects of the design that you can consider as principal. So we can define the models and modeling in those terms. Then an architectural model is an artifact that captures some or all of the design decisions that comprise a system's architecture. Then architectural modeling is the reification and documentation of those design decisions. Now these models are most of the time begin in the head of the architect. So unless there is some way to express this in a way that other people can understand, it becomes very hard to understand, hard to communicate these ideas. So the architectural modeling, okay, once you create the model, okay, whether it is a graphical model or whether it's a textual model, it enables you to share the idea with other people. Other people can relate to it and understand it better when it is documented in a model. And then it becomes part of the project documentation as well. So in a lot of software projects and for quality aspects as well, we have to keep documentation. So these architectural models are also part of that documentation, which will be important for maintenance of the software in the long run. Then how can we model is mainly influenced by the notations that we choose. So the tools that we use. So you might have learned rational rows. So if you're only using rational rows, then you're stuck with the diagrams that you use in rational rows. Same for UML. So in UML2, there are only few architectural diagrams that we can use, and then you have to use only those diagrams, right? So that kind of influence is there, that is defined by the notations that you choose. Then an architectural modeling notation is a language or means of capturing design decisions. So this architectural modeling notation is what we refer as something like the UML, right? So there are UML, there might be other, we will look at these tools later. So these notations, so sometimes you can use PowerPoint diagrams, sometimes you just use plain English, okay, normal language, right, can be used. So whatever the notation, it is just a means. It just gives you a technique to capture the design decisions. That's the most important thing. You just need to capture all the important design decisions here. Then how do we choose what to model? So choosing what to model is another problem we have to address. So architects and other stakeholders must make critical decisions about what architectural decisions and concepts should be modeled, and at what level of detail, and with how much rigor or formality. So these are the main questions that need to be answered when deciding about the architectural models. So what architectural decisions and concepts should be modeled? So as we mentioned, only the principal design decisions should be included in the architectural models. So you don't have to include all the tiny design details, like say a user interface, whether you are going to have some type of a radio button or a combo box. Those things you don't need to specify in the architectural models, right? So then like that, you have to decide what are the architectural decisions. Now if you're going for a client server architecture or a cloud based server, or it's just a standalone machine, or if you need to include a certain software platform for a mobile device, right? So that kind of big decisions you have to include. So that is the first step. Then at what level of detail? So once you decide on the decisions and the concepts that need to be modeled, say if you select that the client server architecture must be modeled, then how are you going to represent that client server architecture? Are you going to give all the hardware details and all the connections and the configurations, which might be too much for a lay person or a business side stakeholder, right? Say the business owner or a board of director, a member of the board of directors of the company. So those people might not understand that. So you have to like decide at what level of detail. Maybe just a high level diagram of the network might be enough for the business stakeholder, business side stakeholders. Then with how much rigor or formality? So rigor or formality means how what tools, right? If you are following UML, so UML is very rigorous, right? You know that UML diagrams have a lot of syntax, right? So you have to exactly follow the syntax when modeling. So that's a rigorous language. So when modeling in these notations, there are rigorous notations and less rigorous notation. So, and the formality. So in now in formal context, where the architectural models need to be approved by the business side stakeholders, or all stakeholders have to sign them to say that they have seen and they adhere to it, they agree to the decisions taken. So then it is more formal. Whereas in another company, maybe it's just for the documentation purposes, and none of the stakeholders might care about the designs, right? So that's another extreme. So there are cases where you have to be very, very formal, especially say government or US government projects. You have to be very formal. You have to get the approval for everything. Otherwise, they might not pay you at the end, right? Or you could get into legal problems, right? So in that kind of formal situations where your client is strict about the formality, so always carefully follow the formal methods of the methodology you are following, so get the documents approved and things. Then in a less formal environment, you can be less formal. You don't need that much amount of documentation to be prepared. So all these are choices for the architectural model. Then these are costs and benefit decisions. So all these, the more documentation you need, more cost is incurred, but there are benefits as well. So there are benefits of creating and maintaining an architectural model, and but the benefit must exceed the cost of doing so. So there is a cost in a general industrial setting. There's cost for everything you do, because the people have to be allocated to work, and they have to work, and we pay salaries, and the company's resources are used. So there's a cost. You can calculate the cost of, like, say, drawing a UML use case diagram. So use case diagrams, right? So how much time will it take you to draw a use case diagram? After within a say, while you are doing an interview of, say, 1 hour, how long will it take you to draw a complete use case diagram? So maybe 2 hours, 3 hours maximum, right? So, but still, that 3 hours is your effort. Say if you are a business analyst, so if the business analyst of the company works for 3 hours, you can cost. So if the business analyst gets, say, 50,000 per day, okay, if the day is defined as 8 hours of work, then how much will it pay for 4 hours? So maybe 25,000 or something close to that. Right? So you can include all the costs incurred. So not only the people cost, the hardware, software, so even licenses. So you have to consider all those cost factors and estimate a cost of doing that model. Then you have to you can calculate the benefit. So especially in quality assurance, we are able to prove that if you follow rigorous methods, then there is a cost reduction, because rework is reduced, because there will be less errors. So you can always calculate how much benefit it will introduce. So using that kind of, there are several methods. We will not go through all about the benefit, how to calculate the benefits in this course, right? We will discuss those things in next semester's software processes. So these are coming under software process and quality concepts, right? So in the end, you have to decide whether it is worthwhile drawing these modeling architectural models or not to draw them. Okay, then when drawing these models, you have to select which of the concerns are we gonna model, because sometimes there might be very important concerns and concerns that are not that important. So here, when you say concerns, these are the main requirements. So we normally identify the functional requirements and the non-functional requirements in the SRS, but these can sometimes be clustered to broad concerns. So if you feel that while talking with the stakeholders, the business side people, the implementers, the test engineers, you will be able to tell which areas will need more attention, which are the areas that are ambiguous or that are not very clear. So the stakeholders have to identify the aspects of the system that they are concerned about. And the stakeholders decide the relative importance of these concerns. It's a relative importance. Now, all the concerns are important, because if the modeling is not done properly for any of the concerns, then there will be errors, there will be bugs in the final software that you create. But then, even then, there are more important concerns and less important concerns. Say something like a UI will be important, but in a normal business application, those usabilities are given less priority, mainly in the architectural modeling. So those UI designing is is most of the time does not become architectural modeling unless it is very critical non-functional requirement. So that kind of things will have less importance. And then the modeling depth roughly mirror the relative importance of the concerns. So the depth that we talked about, so being rigorous and how much uh, information or the level of detail and will depend on the importance as well. So the more important a concern, you will give more details about that requirement or the requirements covering that specific concern. Then let's look at what do we model. So there are the basic architectural elements that you should model once you decide to make a model. So first thing is components. Now we briefly discussed about components in one of our previous lessons, right? So components are part of the software, part of the program. So so for example, in our Lunar Lander game program, in the implementation that we are in the example given here, there is a get burn rate from user component, and then there's a compute new values component, then display new values to user component. So you see these are program components. So these might be in the same file, or they might be in a client server architecture. Some might run on a server side, another might run on another machine. So we are not really interested in where it is running. We are not depicting where these components are situated at, but mainly what the program components are only at this level. Then there are connectors. So connectors create the links between the different program units. So connectors can be method calls, okay, message passing, it can be a network connection, it can be the internet. So various connector mechanisms can be there, but in the end, we should model these connectors as well. Then the interfaces. So at the interfaces between the components and the connectors, right? So between the component and the connector, then again the connector to the component, right? You will have interfaces. So all these interfaces we need to model as well, right? So in this small example, we see that we have 8 interfaces, right? So there are 8 interfaces in between the 3 components and the 2 connectors. Okay, so we just had 3 components and 2 connectors, but we have 8 interfaces, and you have to decide which interfaces are more important or which might have problems implementing. So then you have to give more details and focus on those particular interfaces. Then the fourth aspect we need to model is the configurations. So you know that when it comes to particular hardware, right, you need to configure the hardware for a given software. So here we have to give the configuration details about how we configure all these software components, the connectors, the interfaces into our actual system. So the configuration details are also part of the architectural model. Then the final thing is the rationale. Why you do these things, the reason behind these decisions, right? So for example, if you have a get burn rate from the user component, which is running on the client machine, right? Maybe on a web-based application as a website, then say using Java applets or HTML5 or say Flash or some animation. So then you have to justify why you are doing this, doing it that way, and why that particular model, right? And then the connectors. So you might have to justify why are you using this kind of stream, why not another way of handling, right? So for all the decisions, you must have the rationale. What is the reasoning? So it will be useful later on when you try to maintain the system. Then there are these elements, the components are the architectural building blocks that encapsulate a subset of the system's functionality and or data and restrict access to them via an explicitly defined interface. Then there are connectors. Connectors are the architectural building blocks that effect and regulate interactions among the components. Then the interfaces are the points at which components and connectors interact with the outside world. So in general, other components and other connectors interact with a given component or a connector. So in this figure, we had 3 components, 2 connectors, and we had 8 interfaces. Okay. Then the interfaces are the points at which components and connectors interact with the outside world. In general, the components and connectors. And the configurations are a set of specific associations between the components and connectors of a software system's architecture. Such associations may be captured using graphs whose nodes represent components and connectors and whose edges represent their interconnectivity. So normally in the graphical models, graphical notations that we use nodes to show components and connectors, and the edges, the lines. Okay, the lines that we draw between the components and connectors will show the interconnectivity. Then the reasons behind, or the rationale, is the information that explains why particular architectural decisions were made and what purpose various elements serve. Then the elements of the architecture style include inclusion of specific basic elements. Now remember last week we talked about architectural styles. So there might be domain specific styles, software architecture, DSSA. So in a given domain, there might be some elements that are always used. So if you are following the domain specific, it is a must that you use those elements. So that kind of architectural style decisions are there. Then the components, connectors, and the interface types will depend on the architectural style, and the constraints on the interactions, like the time limitations, the security aspects, will depend on the architectural style that you are using. Then the constraints on the interactions and the behavioral constraints, concurrency constraints, which can run parallelly and which cannot, will all depend on the architectural style. Then what do we model? Right? What are the diagrams we can draw is another thing. So we have static and dynamic aspects. Now in UML, you might have remember we had dynamic diagrams. Right? What are dynamic diagrams? Dynamic diagrams show the system as it runs. So while the system is running, the diagram changes. Right? So that's the concept of dynamic in here. So static aspects of a system do not change as a system runs. So just because the system is running, the static diagrams do not change, right? So for example, all the UML diagrams we have learned in the previous courses. So the topologies, right, the network structures, assignment of the components, connectors to host are things that do not change as the system runs. Then the dynamic aspects do change as the system runs. So there are dynamic things that change, right? For example, state of individual components, right? The state of components, say a program, will change as a, say, even when a variable value changes, the state changes. And the connectors might get switched on, switched off, it might get power, might lose the power. So it comes into different states. And the state of a data flow through a system. So data flow can also have states. So data might be flowing, it might be waiting, it might flow to the other direction, right? So you might query, you might get the results. So you might just be idling. So different states are there. So this line is often unclear. So sometimes it is difficult for us to decide whether you want dynamic aspects or static aspects. So consider a system whose topology is relatively stable but changes several times during system startup. So sometimes there are systems where the structure or the topology of the system is relatively stable, but at the beginning it might require a little bit of setting up configurations, right? So in the real world it is often the case. Sometimes a certain server configuration might not work. So say setting up a firewall, and the IP addresses need to be changed, or the routers need to be changed, the bridges have to be adjusted, so or certain network cabling doesn't work, you have to go for, say, some wireless technology. So then the topology might change because of these practical problems that you might encounter at the beginning, at the startup. Okay, but once the system stabilizes, once the system is used for a longer period, it will be stable and you will be able to run without changing the model. So then you have to decide whether you want to show all the changes or not. So you have to make the important distinction between models of dynamic aspects of a system. Okay, we are talking about models. Okay, there are models that do not change. Models do not change, but the models of dynamic aspects. So you are modeling dynamic aspects like the state charts. In a UML state chart, you will make a drawing of all the possible states that a certain software component can take. But that does mean the state chart has to change. The state chart does not change, but it is showing the dynamic aspect. Then the other thing is the dynamic models. So dynamic models are models that are themselves changing. So it's like a simulation software. If you're simulating what is happening in your software, so then it becomes a dynamic model. So if you have a simulation of your software system, then that becomes a dynamic model. So sometimes that kind of models are used, and then you should know that then it is a dynamic model. Otherwise, if you are just modeling the dynamic aspects of a system using a static model, that is a different case. Then there are functional and non-functional aspects of a system, right? So as you already know, functional requirements are very easy to capture. So you must find words like the system prints medical records. So it's just expressive verbs, right? Then when it comes to non-functional requirements, Usually you find adverbs that qualifies your statement. Like here we have quickly and confidentially. So these adjectives or the adverbs that qualifies uh, are sometimes hard to identify. So in the architectural models, you most of the time find the functional requirements. But like rationale, it is often important to capture the non-functional decisions, even if they cannot be automatically or deterministically interpreted or analyzed. So now it might not be obvious. The non-functional aspects might not be obvious. So unless the business analyst is very experienced, you will have to talk with the client and pry into the details to really understand the non-functional decisions, why they are important, right? Say, let's take an example like you need say you will only allow maintenance to be done between 1 a.m. and 3 a.m. Say, for example, today our LMS is down. So that's why I'm recording the lecture here, but you are not able to connect live. So unlike other days, because the LMS is down at 9 a.m. Now, we might need a non-functional requirement that says the LMS should be maintained only from 1 a.m. to 5 a.m. because that is the time we have least users, least online users, right? So that kind of thing, if you have the rationale and then you understand why it is important to have that kind of non-functional requirement, the maintenance is only done at that particular time, and at other times you want it up and running 24/7. So that kind of reasoning, right, is important. So so we have to capture that kind of non-functional aspects of the system into the models as well, if possible, right? Then the important characteristics of models are that we have to be non-ambiguous as much as possible, right? What is ambiguity? So this is also a term that you have learned in the first years of engineering as well. So a model is ambiguous if it is open to more than one interpretation. So most often architectural models are drawn at a very high level. High level means like without much details. So when all the details are not there, then in the later stages, the designers will decide. The designers or the implementers will have freedom to choose. So inherently, architectural models will have ambiguity. So how to overcome this problem? So it can be a problem when different stakeholders um, uh, assume different things by looking at the same architectural model. Say you have say you have specified a firewall in the architectural model, right? So that firewall might mean different things to the different stakeholders. Say if it is for a banking project, and the bank manager will think that this firewall can stop all the hackers, all sorts of intrusions it will be able to stop. But if the designer thinks that this firewall is only for the database and it is not going to apply for the user interfaces which might run on another server, right? So there might be a mismatch, right? So that kind of ambiguity is often addressed by informal communication, informal agreements between the stakeholders. So meaning the architect or the architectural modelers will discuss with the other designers, the implementers, and the people who will really go on site and deploy. And from the other side, there will be the business analyst also will have to agree, right? So that kind of agreement will make it less ambiguous, right? So then the accuracy and precision. So what is accuracy? Accuracy means you have less errors. So even though accuracy and precision have similar meanings, they are actually different. So accuracy means if something is accurate, that means it is correct and it conforms to fact, right? It is the reality, or deviates from correctness within acceptable limits. So if there are errors, the errors are very minimal. They are within within a small range. Then the concept of precision means that you always give the same result, right? A model is precise if it is sharply exact or delimited. So a precise system can sometimes be incorrect, but it is always giving the same incorrect decision. Then it is precise. Understand? So we look at a graph here. So what is A? Now picture A. Do you think it is precise or accurate? All the points are everywhere, right? So it's not either accurate or precise. Then B has what? B has little bit of accuracy because one of the points have like hit the target in B, right? So but still it is imprecise because it is all over the place. It has not repeated. So it is accurate, okay, because most of the points are close to the center, but it is imprecise because it is ambiguous or shallow assertions are made. Then C, you are off the target, but it is precise. So you are inaccurate but precise. So detailed assertions that are wrong will lead you to inaccurate but precise systems, precise models. Then to get accurate and precise models, you will need detailed assertions that are correct, right? Okay, so this figure summarizes the concepts of accuracy versus precision, right? So if you go through them one by one again, if you use incoherent assertions, incoherent means you don't understand, right? The designers or the implementers will not understand your diagrams. And contradictory, so sometimes one requirement will contradict the other. So in that case, if you like blindly follow the requirements and make the drawings, right, make the models, right, there will be contradictory decisions in your model. So then it becomes both inaccurate and imprecise. Then in the case you have ambiguous drawings, ambiguous models, or you have made shallow assertions about the system, which will not hold when the system is used in the real world. It will test the system and there will be errors. So then the model is accurate but imprecise because you did not consider all the assertions correctly and did not consider all possible settings in the real world. Then when the details are made for the assertions, all the possibilities covered, but they are wrong. Okay, you will flesh out all the details, but you are doing you're thinking wrongly. So then you will draw a lot of models, but it is not solving the problem. So then inaccurate but precise models. Then if you correctly give all the details and make all the correct assumptions, then the models will be accurate and precise. Okay. Then to start with the concept of views and viewpoints. Now generally it is not feasible to capture everything we want. Now you will not be able to capture everything you want in an architectural model because it's going to be high level and you only need to capture the principle, the main decisions only, right? So the model would be too big if you try to capture everything in one big architectural model, and it might be complex as human might not be able to read it and understand, right? So if a model is too complex, now it's true that we are developing complex systems. Your software will be complex, but your model should not be complex, right? And if it is too big, then it will become confusing. So you might draw a diagram that spans say 10-20 pages. There'll be lines running everywhere. So there's a limit of information that humans can comprehend. So more than that, it will just simply confuse the people. So we create several coordinated models, each capturing a subset of the design decisions. So rather than drawing one huge architectural model, we will draw several small models, right? So several coordinated models. So each will look at the same system from different angles. So generally, the subset is organized around a particular concern or other selection criteria. So we call the subset model a view and the concern or the criteria as a viewpoint. Understand? So we call the subset model. We first define the subset or the aspect, the angle, and call it the view. And the concern or the criteria about the subset. So for each view, you might have different viewpoints, right? So subset of the model you select and then select a viewpoint to look at it, right? So you will have different views and there will be several viewpoints for each view. So by combination of different views and viewpoint combinations, you can cover the whole software. So view is a set of design decisions related by a common concern or a set of concerns. And a viewpoint defines the perspective from which a view is taken, right? So view is the design decisions about a concern or a set of concerns, say security. So if security is one of the concerns, you can have a security view. You are looking at the system from security view, and the viewpoint will be different. Now for security, again, there will be several viewpoints for security aspect as well. So for example, let's see if we have a three-tier application, right? You can look at it from a deployment view. Now at the time of deployment, it is important that you identify the components that are installed on the server machine and the components that are installed on the client machine. So that is given in the deployment view. So in the deployment view, we show what are the components that should be in the different hardware. Okay, so in a three-tier application, you have 3 tiers of components. On the server, you have the data, then connectors and the business logic. And same thing in the client machines. You have the client logic, there are connectors, and then there are the client GUI. Then if you take the deployment view of a Lunar Landers game, so which is shown on the right side here. So there are the space system and a ground system. So which are two different machines, could be on a client server architecture, or it could be on the same machine but separate independent systems. So in the space system, you will have sensor drivers, connectors, attitude control, and thrust control components, so different program modules there. Then on the ground system, you will have the ground system controls, the connectors, and the mission planning. Right. So that gives you an idea about the difference between the views and the viewpoints. So both instances of the deployment viewpoint. Okay, so both are instances, both are views of the same deployment viewpoint. Then let's look at the commonly used viewpoints. So the most popular viewpoints that are used in commercial projects include logical viewpoint. So we have to verify whether the program is doing the logically correct thing. We need a logical viewpoint to analyze, right? So in the logical viewpoints, we capture the logical or the software entities in a system and how they are interconnected. But then physical viewpoint is also important. So to look at how the hardware configuration is done. So the physical viewpoint capture the physical entities in a system and how they are interconnected. So all the wired and the wireless networks, the wireless connections of all the hardware components will be viewed as physical viewpoint. Then the deployment viewpoint, as we already saw, deployment viewpoint will identify when you are installing, when you are deploying the software solution, on which machine or which hardware runs which software. So you have to capture how logical entities are mapped onto physical entities.